Welcome back. So in the second lecture, I would like to tell you about light and antiferromagnets. So yesterday, I bombarded you with a lot of equations. So to compensate, today there are no equations in the seminar. So, so yeah. So for some of you, it's a welcome change, I suppose. Right. So let's focus on the use of light to control the properties of antiferromagnets. And maybe for some of you, this may be a little bit of a different way of thinking about light-matter interactions. So normally we think of light as a way to probe material properties. So light is our typical window into the properties of materials. We can use it to probe spectra of phonons. We can look at magnetic excitations with light and so on. Today I would like to bring the emphasis more on using light to bring matter out of equilibrium in order to possibly generate some interesting states of matter that may even not occur in a thermodynamic transformation. So you know that phase diagrams of materials can be very complex. We can have complex energy landscapes, and there may be phases of matter that they can be accessed only through a strongly out of equilibrium excitation that accesses states that would not be available through a conventional thermodynamic set of changes of temperature, magnetic field, electric field, and so on. That's a little bit the concept. And we have a nice zoo of collective excitations that in principle can be accessed using a strong light perturbation. So if you think about excitations in matter that carry an electric dipole, so excitations that couple strongly to electromagnetic fields at first order, we find a number of interesting collective modes in materials. So maybe the first one that comes to mind are phonons. But as we crank up the photon energy that we can use, or the frequency of the electromagnetic light that we are using, we can access a whole number of collective excitation. So yesterday we heard a beautiful lecture about antiferromagnetic spintronics, where there was emphasis on the properties of magnons occurring at gigahertz and terahertz frequencies. And as we approach the visible range, we also have a number of charge excitations that access interesting states of matter. So there's a broad research field that is growing and growing. And today I will give you my own perspective on this. So this is not a review talk. And so let's visualize something concretely. So let's think about phonons to begin with. So we have a material that is sitting at a certain temperature. So there's going to be a certain thermal incoherent excitations of the phonon populations of our system. So some form of incoherent motion that is present. Now, if I'm able to come in with a light pulse that can be tuned in resonance with a specific phonon mode, now I can impinge a very specific coherent motion to my crystal. Okay, so the concept is to come in with a light pulse that can be tuned in resonance with a specific collective mode of the system and bring in a certain organization of its dynamics. Okay, and I like to think about this as an orchestra conductor that at time zero is bringing in some coherence in the dynamics of a collective. All right, and in this talk we are going to first discuss the excitation of phonons in our favorite complex oxides. So we will start with a simple example of an insulating material, lanthanum aluminate, and we will see what happens when we excite phonons at resonance and we interrogate structural dynamics. And I will try to show you that this resonant phonon excitation brings about a number of rearrangement in the structural properties of the system, notably the excitation of Raman phonons, starting from the excitation of an infrared active phonons and the formation of strain waves that propagate across the material. So both longitudinal and shear strain waves. And then we're going to put an epitaxial film on top of lanthanum aluminate. We will excite these strain waves, and we'll see what's going to happen to the properties of this thin film. So this will illustrate a little bit what can happen when we excite resonantly phonons in complex oxides. And we will apply these ideas to the study of a very interesting antiferromagnetic system that is called dysprosium orthoferrite. That is an interesting material because it's characterized by multiple magnetic states that are possible, that are close in its configuration space. So after that, I will contrast the excitation of phonons with the excitation of orbitals. And then we will make an excursion in the world of van der Waals materials, and we will look at the properties of the excitation of orbitals in manganese thiophosphate. So that's an interesting antiferromagnetic system. So all the magnetic systems here are antiferromagnet. And then in the final part of the talk, we will discuss the excitation of propagating spin waves in, again, dysprosium orthoferrite. So how we can accomplish this using light. And this connects, I think, with the lecture that we had yesterday on antiferromagnetic spintronics. Okay, great. So let's start by focusing on phonons. So these are pump-probe type of experiments. So there's a pump and a probe. So a pump is a mid-infrared pulse that lasts something of the order of 250, 300 femtoseconds. And we can vary its frequency in order to hit a certain phonon resonance. Okay, so at first order, we're going to excite an electric dipole and bring about some lattice dynamics. So after this pulse has interacted with matter, we come with a second pulse, that's the probe, and we use this to interrogate structural, electronic, magnetic properties of the material and observe their dynamics. So we can control the delay between the pump and the probe, and this allows us to track in time what happens. Okay. So every time, this is something that is an averaging experiment, right? So you come with the pump, you interrogate with the probe, and you do this again in our lab 1,000 times per second, and you average out your response, right? And you get rid of a lot of noise. Okay, so that's a little bit the approach. And in our lab, we interrogate electronic properties using terahertz spectroscopy. So our probe can be a terahertz beam. We use magneto-optics, so our probe can be the Faraday or the Kerr rotation of a visible light pulse, or it can be second harmonic generation. So we can also use this as nonlinear probes. Right. So now, before we continue, let's ask ourselves a fundamental question. So what type of laser pulse do I need to use in order to induce some significant structural dynamics? Okay. So the laser pointer that I'm using here carries an electric field of the order of 100 volt per centimeter. Okay, and we're all familiar with the interatomic electric fields in our ionic type of materials. So these are hundreds of megavolt per centimeter typically. So this laser pointer, even if it was tuned in resonance with a phonon, is not going to induce very significant changes in atomic positions. So we need to, we would like ideally to have something of the order of 10% of a few percent of this to have some significant atomic motion. That's why we need to build some strong light sources, and in our lab we have chosen to generate mid-infrared pulses through a series of photon down conversions. So we start from the output of a femtosecond laser system that gives us pulses with wavelength of the 800 nanometer, photon energy 1.5 electron volts, and energy per pulse is of the order of 5 millijoule. Okay. And this pulse is used to induce a series of nonlinear optical processes which convert down the photon energy to the desired range. So the first process is a white light generation that is followed by optical parametric amplification and then difference frequency generation. And after this process have occurred, we can obtain mid-infrared pulses with a tunable central frequency between 6 and 18 microns, so that's the wavelengths, which last something of the order of 200 femtoseconds, and carrying an energy of the order of 5 microjoule per pulse. So you see, we started with 5 millijoule, and we end up with 5 microjoule, so we paid a big price to go down in frequency, in energy, but the electric field that we find in these pulses is still of the order of 10 megavolt per centimeter. So at 10% of our equilibrium electric field, so we can think of exciting some significant atomic motions. So why do we need all this juice? So our objective is to create an out of equilibrium state in the crystal lattice in which the atoms are oscillating not around their equilibrium position but along some new coordinate. Okay? So in order to do that, we need to excite some nonlinear dynamics in the lattice. Right? And the most simple nonlinear phenomenon that you can think of is optical rectification. So what we would like to do is not to have an ionic displacement that oscillates harmonically and then decays back, but we would like some oscillations along a displaced zero. All right? And this phenomenon can occur. It was initially discussed in this seminal work. It was, for the very first time discussed much earlier in the maybe 50s, 60s in the literature of Raman scattering. So this is known as nonlinear phononics or as ionic Raman scattering. Okay. So what happens is that the lattice is displaced along a Raman active coordinate, starting from a large amplitude excitations of an infrared active phonon mode. Okay. So if you want, it's a way to induce out of equilibrium lattice distortions. Does this actually occur? Okay, so can we find experimental evidence that this idea is correct? So let's consider the case of lanthanum aluminate, a material with a very large band gap, above 5 electron volt, I believe, and so we are exciting it with laser pulses with photon energies of the order of 70 millielectron volt. Okay, so there's no electronic excitations happening here. So we are focusing on the lattice degrees of freedom. So lanthanum aluminate has an interesting structural phase transition from a high temperature cubic phase above 800 Kelvin down to a rhombohedral structure with an A-, A-, A- pattern of octahedral rotation. So these are anti-phase rotations with the axis of rotation along the 1-1-1 direction of LAO in the pseudo-cubic representation. And this phase transition is accompanied by the condensation of two Raman active phonons. One is the A1G mode, and one is an EG mode. Okay, which go to zero around 800 Kelvin. So there is obviously a nonlinear lattice dynamics associated with the instability of this particular phonon mode. So there's a possibility to have some nonlinear lattice dynamics here. And this was emphasized by the experiments of Jorrit, that now has finished his PhD and is working in industry. So what Jorrit has done in this experiment is taking a crystal of lanthanum aluminate, is exciting it with one of these laser pulse, and then is interrogating the lattice dynamics by looking at changes in reflectivity of a 800 or 400 nanometer laser beam. Okay, and what he sees is that if he's exciting the system off resonance with a 10 microns wavelength pump pulse, he sees a very incoherent and rapid decay of the signal. However, if he chooses to tune the laser light in resonance with this particular mode, occurring at close to 15 microns, so this is a aluminium oxygen stretching mode. So this the aluminium is moving inside the oxygen cage, as illustrated here, then what you already see is this very large amplitude coherent excitation. So this is so he's exciting the lattice with a 20 terahertz pulse, and he's observing coherent dynamics occurring at 1.1 terahertz. Okay, strongly nonlinear coupling between phonon modes. Okay, so this 1.1 terahertz mode corresponds to this A1G mode that is associated with the structural phase transition in the rhombohedral low temperature phase. Okay, and this mode looks like this. Okay, so before I showed, so we are exciting a aluminium oxygen stretching inside the octahedral cage. What is happening here is that the whole cage is doing this coherent motion. Okay, so it's changing is octahedral rotations. So now you tell me, is this, what type of excitations I can imagine now to a hypothetical electron system in a perovskite material that is undergoing this oscillation. So I remind you, as I showed you before, the rectification entails an oscillations of this Raman mode in around a displaced position. So this is not oscillating along our equilibrium octahedral distortion, but there is an additional octahedral distortion, and now we're oscillating around that. So can you imagine something that can happen to materials when you do that?
Maybe you excite, for example, a polar mode in your material, and then it processes, let's say, or it's some sort of an optical rectification which is similar to the visible light.
Yeah.
And then because of that, you somehow make the lattice ring into like second order nonlinear process.
Yeah.
In the
yeah. Right. Yeah. So this is precisely what's going on here. And I'm also thinking about changes in material properties that I can induce doing this. So we know that oxygen octahedral rotation, they govern a lot of fundamental parameters, hopping integrals, magnetic exchanges, the typical parameters that govern the properties of a material are strongly influenced by this atomic arrangement. So this is a way to perturb possibly the electronic properties of a material. So lanthanum aluminate obviously doesn't have any magnetism, so that's a, let's say, a simple example to look into this. But I like to use it as an illustrative starting point. All right, so that's first thing that happens. We are excited these Raman modes out of equilibrium. Second thing that happen has to do with a phenomenon called electrostriction. Are you familiar with this? Yeah, so this is it's something that it's not always known to people when I talk to them. So that's a change in lattice constant of an insulating material in response to an electric field. So that's not a piezo effect. So that's a much stronger. It's a poor man version of the piezoelectric effect that occurs in a variety of insulating systems. In lanthanum aluminate, electrostriction is actually quite important. I like to illustrate it with the example of lanthanum aluminate on strontium titanate. So a few years ago, we did this experiment at a synchrotron facility where we showed that because of electrostriction, lanthanum aluminate undergoes a 2% lattice expansion with an electric field of the order of 20 megavolt per centimeter. So that's a pretty big change. Okay, so lanthanum aluminate undergoes this electrostrictive phenomenon. So what happens when we are exciting the system at resonance? Right. So you may remember from electrodynamics course that associated with a resonance there is also penetration depth. So there is an extinction of the electric field that is penetrating inside the surface of the material, typically a few hundreds of nanometers. So there is a strong asymmetric profile of electric field. Now there is decay inside the material when it's been excited at resonance. Okay, and these are electric fields of the orders of tens of megavolt per centimeter. Okay, so the material inside this slab at the surface is undergoing an electrostrictive response, which will cause a lattice expansion. And so when the laser light is reflected out, we are left with the slab of the material that is expanded, right? And this is, an excitation of a acoustic mode. So this slab here starts propagating inside the material at the speed of sound. How do we observe this propagation? So it's a pump probe type of experiment. So we come with a second light pulse that is reflected, and it is reflected both by the surface of the material and by this propagating wavefront. And as these two light probes have been reflected, they undergo destructive and constructive interference as this object propagates inside the material. So every time a quarter wavelength of the probe is propagating inside, we have an interference fringe. So we can follow the propagation of this mode for a long time. Okay. So that's one of our data sets. And you see that if you take the Fourier transform of this oscillation, we actually see the propagation of two modes. So from the position of this peak, you can actually measure the speed of sound. Okay, and this mode here corresponds to the longitudinal speed of sound of lanthanum aluminate, which is 4.8 kilometers per second. And this peak here corresponds to the transversal speed of sound, which is 6.7 kilometers per second, which match perfectly the literature. Please.
So in your case, the material is not doped, so you're not doing any kind of Joule heating, nothing.
Right. In a sense, there is some heating, so we are depositing an excitation in the system. So yeah. So exactly. So let's say we are depositing energy in the material in very specific excitation channels. So this question comes often. Are you heating the material? What are you doing? So I think it's always a good question to ask when you're looking at an out of equilibrium experiment. But I like to differentiate between incoherent electronic excitation that are depositing electron volts of energy into the system that then decay over a variety of channels in an uncontrollable way, with excitations in which you take in a photon energy that is well selected to couple to specific degrees of freedom and is exciting some interesting dynamics. So both are exciting your material, but one is giving a big hit with a hammer, and another one is touching a specific lever. Okay, that's a great question. Thanks. Yeah. Any other questions? All right. So let's also look a little bit more about. I don't know if I want to show you this. Okay. Yeah, let's do it. There is a subtlety that we still are studying. So the excitations of these transverse and longitudinal propagating strain waves can be strongly influenced by coming in and out of resonance of this phonon mode. So we are always exciting both modes, but the efficiency in which we excite the longitudinal mode and the transverse mode depends strongly on the exact photon energy that we are using for this experiment. So when we are tuning, so this peak is the phononic resonance that we are exciting, and here you see the amplitude of the longitudinal mode and the amplitude of the transverse mode, and the two seems to be competing with each other. So one peaks and the other one has a dip. Okay, so that's an observation. We still don't understand it. And if you have a good idea on how we can go further, I appreciate talking with you. Right. So that's a summary of what we see. When we excite phonons at resonance in perovskite materials, we typically generate an excitation of a coherent Raman mode that is oscillating around a displaced position. And we observe typically longitudinal strain waves, and in some materials we observe also a transverse or shear strain wave. Okay, so that's our starting point. So what can we do with this? First thing that we could do, so we're exciting a strain wave. Can we put a material on top, epitaxially grown, so nicely strained and observe some dynamics on the thin film by exciting the substrate. And so we did this experiment a few years ago by looking at neodymium nickelate grown on lanthanum aluminate. Okay. So this is a 1-1-1 grown NNO on a layer. You're probably all familiar with the physics of the nickelates. Let me just remind you that these guys, they have a very sharp metal to insulator transition with a temperature of this transition that strongly depends on the mechanical boundary condition. And in the insulating state, we also have a very interesting antiferromagnetic order. So associated with this electronic transition, there is a structural distortion. So that's described by breathing mode. So so we go from an orthorhombic to a monoclinic phase. So in the low temperature monoclinic phase, we have the nickel sites that are surrounded by either a small or a larger oxygen octahedron. So there is a breathing distortion that stabilizes a checkerboard pattern of small and large oxygen octahedron. So the local density of states here is strongly modified by this, and you have two inequivalent nickel sites. So it's been known for a long time that if you can squeeze your material, if you can apply hydrostatic pressure or epitaxial strain or other forms of lattice control, you can strongly affect this metal to insulator transition. So there's this nice experiment from the 90s where they were applying pressure to neodymium nickelate and widely tuning the transition temperature. So the question is, can we now do this interesting lattice excitation and observe some changes in the properties of neodymium nickelate? Neodymium nickelate across its metal to insulator transition has a big change in its optical properties, as you can imagine. So in the metallic state, we have a well-defined Drude response, while in the insulating phase, this Drude peak disappears, and the spectral weight is transferred to a infrared band, which is very large. Right. So we use this trick to probe the electronic properties out of equilibrium using optics. Okay. Moreover, the nickel sites, also the neodymium sites, they order antiferromagnetically in a quarter wave vector. So the origin of this unusual antiferromagnetism is still, I would say, not fully understood. There's one proposal of non-collinear antiferromagnetic order, while there are other theoretical proposals of site-selective multi-insulators, a bit more exotic. But the bottom line is, in the AFM state, there is a quarter order that appears. That can be revealed by using resonant soft X-ray scattering. So that's an additional technique to the ones discussed yesterday for probing antiferromagnetism. So that's a technique that you can only do at large chaos facilities at the moment. So you come in with a photon energy that is resonant with either an L2 or L3 transition, and then you have a scattering chamber, and you put your detector at the quarter reflection, and at the right photon energies, you're going to see some sharp peaks. So these peaks can be shown to be purely magnetic in origin. So this is really a probe of antiferromagnetism using this high energy light. Right, and so the idea of the experiment is to excite the phonon mode of the substrate. So here I'm showing you at the same time the phonon peak of neodymium nickelate and the phonon peak of lanthanum aluminate, plotted as a function of the penetration depth. And you see that these two are well separated. So we can tune our excitation light to be resonant with one or the other. So we can specifically address the lattice of the substrate. And if you do that, you're going to see, for example, by probing with ternary spectroscopy the conductive properties of this thin film, that at equilibrium you have a well-defined insulating state, and when you excite the lattice of the substrate, the thin films respond very rapidly. Within a picosecond, it becomes metallic. So you have a change of several orders of magnitude in the optical conductivity of the system. So we can really see a transient metallic state by this laser excitation. So what about the antiferromagnetic order? What's going on there? So in order to probe antiferromagnetism, we had to go all the way to the United States, to the LCLS. So that's a facility that allows you to probe your system with pulses of X-rays that can be, at the time, that could be of the order of 200 femtoseconds. Now the new generation light sources, they are aiming for femtosecond type of pulse lengths. So that's a future development. So in the future, we could even probe this type of dynamics with much more detailed temporal resolution. This experiment was done about 10 years ago with 200 femtosecond resolution. So the idea of the experiment is very simple. So if we excite the lattice of the substrate and we induce some variation in the properties of the antiferromagnetic order in the thin film, there is an interesting scenario in which, by exciting a strain wave here, we start to excite first the first few layers at the interface, and then this will generate a propagating excitations across the film. Okay, and the idea of the experiment was to probe the volume of the scattering response in momentum space. So you probably all, many of you do thin films. So you do X-ray scattering, and you're used to look at finite size effects, finite size oscillations around your Bragg peaks of the film. So this is the same idea. So let's look at the finite size oscillations, how they vary over time when we do the excitations. Okay, and that's what we observe in the experiment. So before the excitation pulse arrives, we have a scattering peak that has this finite size oscillations around it. So that's reflecting a very well ordered, sharp interface. So a well-defined thin film carrying this antiferromagnetic order. But if you now measure the same peak 3 picoseconds after you have excited the material, not only you have lost a lot of intensity, so you are disordering the film, but you're also changing dramatically the width of this peak, which is becoming a blob. And then if you let time go by, the system gradually recovers its finite size fringes. So you can Fourier transform this data to obtain a spatial shape of your order parameter. So before the laser pulse comes, you have a sharp interface between the substrate and film, and then as time goes by, you're moving this interface inside, and it's becoming broader. Okay, so this is reflecting a propagating phase front that is moving across the film. And by doing this experiment, you're actually tracking the speed of propagation of this phase front into the thin film. And we see that this exceeds the speed of sound quite considerably. So it's a supersonic propagating phase front. All right, so that's something that you can do. We've also done synchrotron experiments in which we looked at the structural properties when we were exciting this, and we also see that the monoclinic distortion is also being lost during this propagation. Okay, that's all. Maybe okay, it's interesting to me, but it's still melting. Okay, so we are still hitting the system and looking at something getting disordered. Okay, now something that I really wanted to do was to find a way to use this excitation to move from an ordered state to another. So can we use light to not just disorder the system, but to accompany it towards a competing state that also has a broken symmetry. Okay, so that was our goal. And I think this connects nicely with what was discussed yesterday for the field of antiferromagnetic spintronics. So we have antiferromagnet that in principle would allow us to process information at terahertz frequencies. They are characterized by this spin gap, which is set in antiferromagnet in the terahertz range. Moreover, the dispersion of these systems, they tend to a linear behavior as we go to the edge of the Brillouin zone, which a characteristic group velocity of the orders of tens of kilometers per second. In principle, these are objects that would allow us to transfer information very fast and possibly even in a ballistic propagation. And there's a lot of research, and yesterday it was nicely reviewed. From the point of view of optics, there's a lot of work on antiferromagnetic systems and exciting coherent spin dynamics, but optics typically excite a uniform antiferromagnetic spin precession. So yesterday we saw this defined very rigorously, so I don't need to write any equations today, but so the typical oscillations of this modes is something that does not entail a propagation when we're looking at optical experiments. Okay, so and I would like to show you that it is possible to have some propagating effects also using light. So the material that we will use for this study is dysprosium orthoferrite. So this is an orthorhombic perovskite system that is characterized by an antiferromagnetic order of the ion 3+ that occurs below 650 Kelvin. And we have the typical orthorhombic PNMA structure. However, at low temperatures, there is a purely magnetic transition between a low temperature collinear antiferromagnetic state, which is depicted here. So where you have a collinear state along a specific axis, and just above 51 Kelvin, the system reorders to a state that is called a weakly ferromagnetic state, in which the spins, they rotate, so they reorient from the y-axis towards the x-axis, and they acquire a canting through a Dialoshinsky-Moria type of interaction. So we start from a state at low temperature that has 0 net magnetization to a state at higher temperature that has a net magnetization. So this phase transition is of the first order. So it's characterized in configuration space by the competition of 2 minima that is reversed as a function of temperature. Okay, so you go from this collinear state to this non-collinear state. And the barrier between these two states is of the order of a few millielectron volt. Right. So our idea was the following. Can we now excite the lattice, bring our oxygen octahedra out of equilibrium, create a crystal structure that has a certain lifetime, and this will entail a modification of the antisymmetric superexchange between iron and dysprosium, which in turn will modify the energy landscape and possibly induce a transition between these different states. Okay, so that's the idea of the experiment. And I already explained this, but I need to add an extra ingredient to the experiment. So we want to be able to probe an evolution of the magnetic potential that I showed before over time after we excite the lattice. How can we do this? So we know that the curvature of this potential will be reflected by the oscillation frequencies of our spins. So this was discussed very nicely yesterday. Okay, so if we can track spin precession over time when we excite the lattice, we in principle have a way to probe the curvature of our magnetic potential. So for this reason, DIMA has developed a pump probe setup in which we were probing the magnetic properties by means of Faraday and Kerr rotation. So in a Faraday experiment, you're using a probe pulse that is transmitted across your sample, and you track the rotation of the polarization of this pulse over time. So in a time resolved fashion. Okay, and in a Faraday rotation experiment, you are probing the component of the magnetization of your sample that is projected along the propagation direction of the light. Okay, so now I'm going to show you a series of measurements of the Faraday rotation. So you can think of this magnetization component that is probed by the light versus time. And look at what happens when we excite with a pump pulse that is off resonance with respect to the phonon. So here is a phonon resonance, and now we are hitting the system with a photon energy of 165 millielectron-volt. Well, in the Faraday rotation measurement, you see a well-defined oscillation that decays back to equilibrium in a few tenths of picoseconds. So this corresponds to a magnon mode, which is located around 160, 170 gigahertz. So that's a direct probe of the curvature of this magnetic potential. What happens if we now tune the light to be resonant with the phonon mode? Well, one thing that happens is that your amplitude of the oscillation gets bigger, okay? But more importantly, you see that the frequency of this mode has significantly changed. So now there is a red shifting of this frequency down to 120 gigahertz or so. So this is directly telling us that we are softening the magnetic potential by exciting the phonons. You can do the same experiment. So this is measured in the low temperature collinear antiferromagnetic state. You can do the very same experiment in the high temperature phase where your system has this weakly ferromagnetic state. So for some magic, now the lifetime of the magnon mode becomes much longer. Okay. I still personally don't understand this phenomenon, and I haven't seen this addressed properly anywhere. But for some magic, magnons in the high temperature non-collinear state becomes much longer, which is convenient for experiments. But okay. And here I'm contrasting again what happens when you are off resonant and when you are resonant. And you see that this time we have again a change in the frequency, but this time we are hardening the potential. It's becoming faster. So you can do this experiment at various photon energies, and in the high temperature phase and in the low temperature phase. And you see systematically that as you approach the phonon resonance, you either soften your potential or you harden your potential, depending on which phase you are. Okay, so this is telling us something important. We are changing the magnetic energy landscape when we are exciting the lattice, when we create this out of equilibrium crystal structure. So importantly, we need to establish how long it takes to go back to equilibrium. All right, and in order to do so, we just let the system ring down and we wait. We probe longer and longer time delays. At early time scales, we see a frequency of the oscillations that is fast, and then you see gradually that the frequency of the oscillation decays back to the equilibrium value dictated by the curvature of the magnetic potential. Okay, so if you want, you can take a Fourier transform of this data at different windows, different time windows, and you see that gradually your frequency recovers back the equilibrium frequency, and this is shown here. So this decay back. So it takes hundreds of picoseconds for the magnetic energy landscape to go back to equilibrium. However, it only takes a few picoseconds for the magnetic energy landscape to change. All right, so this is telling us that we are really creating an out of equilibrium state with a reconfigured magnetic potential. And what I'm showing here is actually the result of our analysis of all these frequencies versus time, which allows us to really reconstruct the shape of the potential at equilibrium and out of equilibrium. Okay, and what you can see is very interesting. So at equilibrium, your ground state here is, let's say, the system is in an energy state that is well below the energy of the competing state. However, when we excite the system, we bring it out of equilibrium, the system is suddenly in a metastable state. Okay, so in principle, there is another competing minimum here where the system could flip. So in principle, if we hit the system hard enough, maybe it's possible to go from one minimum to the next. And that's what we are showing in this measurement here. So this is again the Faraday rotation versus time. So at equilibrium, there is no Faraday rotation. The system has no net magnetization. But when we hit the system with a strong laser pulse, the system starts to develop a net magnetization. So you see that it starts to oscillate, but now it doesn't oscillate around 0. It starts to oscillate with a finite net magnetization. So this is telling us directly that we are moving from this antiferromagnetic state to this non-collinear antiferromagnetic state with a net magnetization. The transition from one state to the next occurs within the first cycle of the spin precession. It's a really a very fast transition within a few picoseconds. You can contrast this with an excitations of the electronic degrees of freedom. So this goes back to the question, are you heating the system or not? So you can take the same material, and instead of exciting the lattice, you can excite a charge transfer resonance at much higher photon energy of the order of 2.3 electron volt. And you see that with these electronic excitations, you indeed, again, excite a spin wave that oscillates around 0, and then heat is being redistributed into the system, and it eventually reaches the lattice degrees of freedom, which excites the system across the phase transition, and the system starts to develop a net magnetization. Okay. And this takes something of the order of 100 picoseconds to occur. So you need to diffuse heat across your system. This is in contrast with what happens when you directly heat the phonons, where within the first cycle of the spin precession, you have your phase transition. All right. How much time do I have left? Mr. Chairman? Perfect. Okay. So including questions. Yeah. So I can talk for another 15, 20. Yeah. Perfect. Thanks. It's plenty. Perfect. Okay. So now let's make a little excursion now on the world of van der Waals materials. So we discussed resonant phonon excitations. Something that you may wonder now, is this a magic bullet that I can use for any material? I excite the phonons and I start to see, coherent oscillations of magnons, and are there some material-specific properties that are necessary in order to have this type of physics? Okay. And for this, I would like to contrast what happens when we are hitting phonons in magnesium thiophosphate, and when we are exciting orbital resonances in this material. Right. So magnesium thiophosphate is a kind of a useful material for magneto-optics because it's a system that undergoes a transition to an antiferromagnetic state at around 75 Kelvin. And in this low temperature antiferromagnetic state, the spins, they cause a breaking of inversion symmetry, which results in a very large second harmonic generation occurring in the low temperature phase. So we have this nice optical probe of this antiferromagnetic transition. So we send a probe pulse oscillating in frequency omega, and we measure the frequency to omega. And we can do this when we excite with the pump either a phonon excitations or an orbital excitations. All right. So these are measurements done by Matthias, which is tracking second harmonic versus time after he excited this specific lattice mode of manganese thiophosphate in the antiferromagnetic state, and you see that there is a change in the intensity of the second harmonic signal, and you see interestingly that now you are depressing your signal, so you are strongly reducing the antiferromagnetic order, and you do so in a space of 100 picoseconds. You are disordering your antiferromagnetic lattice. Okay, so this is in contrast with all the coherent dynamics that I showed you before in the system. So what's so different between these two systems? So in this material, manganese 2 plus in its ground state is in an orbital singlet state, which is L equals 0. And this is due to the fact that we have 5 unpaired spins. So we have a final spin, 5/2, but the orbital part of the system is in a singlet L equals 0. Okay. So the system has strictly zero spin-orbit coupling at equilibrium because there is no orbit. Okay. So in this material, a resonant Fourier excitations is only leading to thermal spin disorder. Okay. This is in contrast with the dysprosium orthoferrite case, where the dysprosium atom is bringing about strong spin-orbit coupling effects. In particular, this antisymmetric super exchange or Yaroshinsky-Moria interaction, which is giving us this spin counting and this strong sensitivity of the lattice and magnetism, strong coupling of lattice and magnetism. Okay, so that's one of the key points of the, if you want, of the seminar. You need spin orbit. However, in manganese thiophosphate, you can play a different game. So this system has some specific optically allowed transitions that reconfigure the orbital manifold. There is in particular this T1G transition, which brings about a reorganization of the electronic structure, which now gives an angular momentum to the orbital system. So if you excite this particular excitation, your system suddenly realizes that there is an angular momentum. This suddenly reorient the magnetic anisotropy of your system, and this can cause a spin precession. And that's what Matthias is measuring here. So suddenly at time zero, we are exciting the orbital degrees of freedom, and the system develops this nice coherent oscillations of the spins measured through second harmonic generation. Okay, and you can see the temperature dependence of this object of both the frequency of the amplitude that are quite peculiar. So this is the result of an impulsive torque that we have imposed on the spin system by suddenly reorienting the magnetic anisotropy by activating an orbital angular momentum in the system. So an L equals 0 system, has interesting orbital dynamics excited by light. All right, and now I come to the final part of the talk about propagating spin waves. So yesterday we heard a lot about the importance of finding experimental ways to excite propagating angular momenta in antiferromagnetic systems. And a question that we asked ourselves, can we find a way to do this optically? And in principle, you have a big problem, because optics is something that excites your system at the center of the Brillouin zone. So it's hard to directly convert light into a propagating spin wave mode. However, after doing a lot of experiments with resonances, we realized something that we found quite interesting. So if we can find, the idea is the following: if you can find a resonant mode that has a penetration depth that is way below the wavelength of a specific excitation that you're interested in, then you have a chance of confining your excitations over a very thin skin depth inside the material, and this can provide a certain number of Fourier component to a propagating wave packet. So the idea is, can we scan our materials and find an optical resonance with a penetration depth of let's say 50 nanometer or below. So we know that the wavelength of the spin waves that we study are typically in the hundreds of nanometer range. So if you can find an optical resonance that is 50 nanometer or below, then there's a possibility of really exciting a wave packet that has a certain number of Fourier components, and this can realize a propagating spin wave. So that was the idea. And we found in dysprosium orthoferrite an optical absorption line occurring in the, let's say, 3.5, 3.6 electron volt range, which goes below this 50 nanometer range. So that's a very sharp optical absorption line. And microscopically, this corresponds to an excitations of electrons from oxygen states to ion states. Okay, but this is something that decays quite rapidly. So these are very broad optical lines. Right. Okay. So let's assume that this is possible. This idea works. We still have the problem of detecting a propagating spin wave. Okay. How can we do this? So normally, when we do a Faraday rotation experiment, we are only probing uniform spin precession. So we are transmitting light across a sample, and transmitted light is only sensitive to a uniform spin precession mode with Q equals 0. Okay. However, if you now move to a Kerr rotation detection scheme, now you can look at your experiment in a different way. Now you can think of a propagating spin wave in your system a little bit as a diffraction grating. Okay, so light that is being reflected here is going to be sensitive to a certain component of a propagating wave packet according to the Bragg condition. Okay, and so in a Kerr rotation geometry, in principle, you can also observe a non-uniform spin precession mode. So this is routinely done for phonon modes. So this is called the Brillouin scattering in for propagating phonon modes. But as far as we know, it was not tried before for spin waves. Okay, and this is an experiment that was done by Jorrit. So here, at the same time, we are probing in this dysprosium orthoferrite that has been excited at this particular resonance, both transmission and reflection. Okay, and you see that in the transmission mode, Jorrit is measuring through Faraday rotation oscillations of the uniform spin precession mode at 175 gigahertz. However, if it turns on the detection in the reflection scheme, now it sees an oscillations occurring at 225 gigahertz. So what's going on? Why do we see two completely different frequencies happening in our sample? Well, in this detection scheme, we are sensitive to a uniform spin precession mode only, while here we are sensitive to a specific component of a propagating wave packet that satisfies the Bragg conditions, which in this case is this 225 gigahertz mode. So this corresponds to a wavelength of the spin system oscillating at with a wavelength of 140 nanometer, according to the spin dispersion of this system. Okay. So and while the low frequency corresponds to this uniform mode at k equals 0. Okay. So that's the key message here, that by confining the excitation over a sub-wavelength slab at the surface of your material, you're exciting a certain number of Fourier components of a propagating wave packet, and we can probe specific ones by changing the experimental geometry. And then, so we perform all the necessary checks, but in particular, what I found that was particularly important was to demonstrate that we can detect different components of this propagating wave packet. And so this can be varied by changing the geometry of your sample, so cosinus of gamma prime here, and by changing k. Right. And so this is the result of our experiment. So these are different detection of propagating components of the wave packet performed in different experimental configurations. So those are the colored dots. The line that you see on top is not a fit. The line on top is the spin wave dispersion of this dysprosium orthoferrite that is known from literature. And, this convinced us that we're actually detecting various components. And so this type of experiment allows us to establish also the propagation speed through the derivative of the dispersion, and we see that these components of the wave packets are traveling at a speed of the order of 12 kilometers per second. So this is 3 times the speed of sound in the material, and we're only a factor of 2 below the theoretical limiting speed that is possible for the propagation of the wave packet. So you can see that we can only pick a small section of the dispersion because of experimental constraints. So we need to be able to have a magnetic field applied on the sample and come with the light in and out of the sample in a reflection geometry. So we are setting up a new cryo-free optical system that will give us much more flexibility both in the strength of the magnetic field and the experimental geometry. So hopefully we'll be able to map this even better in the future. What I would also like to stress is the importance of this penetration depth being very short. So here I'm showing the detection of propagating mode done by exciting the systems in a range in which the penetration depth is very small, and by exciting the system in a range where the penetration depth is 3 times larger. Okay, and you see that if the penetration depth is large, you detect no propagating mode whatsoever, while you have a well-defined propagating mode if you satisfy this condition. So penetration depth way below the wavelengths. And these are various data points measured for different size of the penetration depth. So confinement is really fundamental to have propagating mode. A final experimental point, you can ask for how long this propagating wave travels for. So you can just sit and let it ring down. We are lucky that in this high temperature non-collinear antiferromagnetic state, magnons are very long lived in the system. So we can track this oscillation for a long time, and we see that for hundreds of picoseconds this keeps ringing. We have a velocity of this propagating wave packet, so we can estimate the distance over which this wave is traveling, and we find something of the order of a micron. So these waves, they propagate ballistically with a velocity that is supersonic, 3 times the speed of sound, 12 kilometers per second, and they propagate over macroscopic distances. Right. So what is next for this research? So one direction that we are very excited about is light matter hybrids. So now we are working quite a lot in embedding our favorite materials within electromagnetic cavities. So this should accomplish 2 goals. One is to enhance light matter interactions at sub-wavelength dimensions, and second, the presence of electromagnetic cavities can induce a reorganization itself of the properties of the materials, even in the absence of light. So that's a theoretical proposal that has been put forward by several groups, and it's something that we should be in a position to test at some point. Right. So let me give you the references of the papers that I discussed today, which are here. And I would like to thank all the members of the group that have been pushing for these experiments. And I would like to thank our theory collaborators that helped us a lot in the analysis of this data, in particular Boris Ivanov in Kiev, Eric Bousquet in Liège, and Roberta Citro at CNR Spin in Salerno for these experiments. And thank you very much for your attention.